Alright, so here's the next section of Chapter 7 involving the concept of what similar polygons are. Here's where we're going to start really getting into the meat of this chapter, what we're kind of doing. So, similar polygons are polygons that have the same shape, but not necessarily the same size. A perfect way to describe this is if you've ever taken, used a photo that you wanted to use in a like a report or a Word document of some kind. So you copy and paste off there, and now you insert it from that was saved. And you decide, like, no, I want this to be a little bit bigger. I want this to be a little bit smaller, or whatever you want to go with. You generally don't just click on only the width side to make the width larger, or only the length side to make the length larger or smaller. You generally click on the arrow in the corner to help resize it evenly for length and width. The reason why is if you don't do that, it gets really distorted. What you're essentially creating is that new picture is a similar polygon in shape to the previous one. It's the same shape, but it's different sizes. Lengths or sides are all different. So you'll notice the key with these polygons, similar polygons, is that all the angles will be congruent, the ones in the same spots at least, but the sides will not be congruent. It obviously makes no sense for sides to be the same if now I have a totally bigger shape or a totally smaller shape. Instead of being congruent, instead the sides will be proportional to each other. There'll be equal ratios for all the sides. The ratio between the sides will be called a scale factor for these polygons. So sides and angles will match up in a very similar way to how we saw them with congruent triangles in Chapter 4. And in fact, when we solve problems later on today, angles you'll still solve the exact same way. Angles are equal to each other. So set the correct angle measurements and then solve your problem. Sides, the key is you have to set proportions. There's very, very few problems in this entire chapter that allow you to say sides are equal. For the most part, 99% of the time, they're not going to be equal. They're going to be proportional to each other. So first, let's practice setting up all this stuff. So for this example, we were told that this triangle, CHF, is similar, that's what this symbol means, similar, to triangle YWS. So I need to know, well, which angles should match up with each other? Well, if we remember back to Chapter 4, how we match up angles from congruent triangles, we look at the similarity statements. First letters should match with first letters, so C and Y are both equal. So angle C is congruent to angle Y. Middle letters, H and W, those are both the next two. H and W are both congruent. And then finally that leaves our last letters, F and S. They are our last pair of angles. So you don't want to try and match them up based off, okay, these two angles are both up top, they're for the same, these two are both on the right side, that's why they're the same now. You take a look at the similarity statements and see, well, which ones in here cause me to actually have my congruent triangles. So, from there, we want to now match up our different sides. So, again, we take a look at the statement. CH should match with YW. So, CH is not equal to YW, but the ratio of that is equal to now the next side, HF, over WS, last two letters, and then finally CF, first and last, over YS. Should be an F, CF. So that's why those two are going to match up. Now, in order to mark it on your triangles to help you solve problems later on, we don't want to use tick marks for the sides, because those implied congruence. Instead, what I'm going to do is I'm going to use a little dot. So draw a dot on CH. There should be a single dot on YW. If I draw a double dot on HF, there's a double dot on WS. If I draw a triple dot on the last side, CF, there's a triple dot on the last side, YS. Now you don't have to use dots, it's just simply what I use to help visualize which side should match up. I don't want to use tick marks because I know the sides aren't equal. They are different lengths. But I do want to show which side should match after I use the statement. So you're going to use these concepts to solve the different problems for the missing angles or the missing sides. So for this one, what I want you to do is on your own, identify which sides are all proportional to each other and which angles are all equal to each other. So go ahead and pause the video while you set up the angle side proportionality statements, and then we will compare results. So go ahead and pause. Okay, so you should be getting this result. So these are the angles that all match up: J with P, H with Q, F with S, M with T. And then matching up the sides, JH over PQ equals HF over QS equals FM over ST equals JM over PT. Those are all the sides that should match up as proportions. You don't have to mark the diagram. If you have all these statements, diagram marking is not really necessary. It does help for those of you a little more visual rather than just simply writing down letters to be able to see what's happening. So it's your call. So we're going to use this information now to solve these different problems. So we're told triangle ACB is similar to triangle EDF. And I want to use this information to solve for the variables X and Y. So if we take a look at Y first, Y is part of angle E. Well, according to our statement, angle E, the first letter should equal angle A. So 11y plus 4 should equal 55. So when we subtract 4 from both sides, 11y equals 51. When I divide both sides by 11, you'll find y to equal 4.63, where the 6.3 is repeating. So you can leave it like that. You also could write it as 4.636. Both are correct. You also could have left it as the fraction 5/11. Again, as long as it's mathematically correct, it's fine. The key is making sure you don't round too much. Like, don't tell me 4.6, that would be wrong. Now, so that's Y. X is part of angle D. Now, angle D, second letter, equals angle C. But the problem is, I don't have a value for angle C yet. Not to worry, though. We do have two angles of this triangle. We do know that all three angles equals 180. So if all I have to do is just simply add those two angles together, 55 plus 85, which equals a total of I have different numbers in my book. That's what messed me up. Okay. That equals a total of 140. Therefore, the missing angle, 180 minus 140, has to equal 40. So that's what we're going to solve. We're going to set angle D, 7x minus 3, equal to 40. Has to be the missing angle. It should be 40. So to solve, we have to add 3 to both sides. 7x equals 3, 43. When we solve, we need to divide both sides by 7. And again, you can leave your fraction as 43 over 7. That's perfectly fine. The decimal rounded properly would be 6.143. That would be the proper rounded decimal. So if you're looking for a angle measurement that's not given to you, you can always solve for that. That's perfectly fine. You don't need to be given all 3 angles. You only need to be given 2 of the angles to solve. Now for this one, this other case is now when we're dealing with sides. So here's a situation where it probably is best to set up using your dots before you worry about setting up your portions. So this 12, the only known side in this triangle, let's try and match that one up first. RT is first 2, so is ML. So 12 matches with 4. Let's solve for X next. X is TS. Last 2 matches with LP, which is 6. So X plus 5 over 6. So this is a proportion. The other one, involving Y, process of elimination and the statements, RS, MP. And we can't use Y in this proportion, but I'll use it again with the 12 over 4, because I know both those fractions. Y minus 4 over 3. Now the nice thing is, this fraction, 12 over 4, can be reduced to 3 over 1. This now makes our cross multiplication much easier. 3 times 6 is just 18, and 1 times any quantity is just that quantity. So 18 equals X plus 5. When you subtract 5, you get 13 equal to X. As for Y, same concept. We know 12 over 4 is reduced to 3 over 1. Cross multiply. 3 times 3 is 9. Again, 1 times any quantity is that quantity, so 9 equals Y minus 4. We add 4 to both sides, and turns out Y is also the same number of 13. Don't let that bother you. If they're the same numbers, it doesn't matter as long as your mathematics was correct. So those are the 2 types of similarity problems you're going to see. Either you're going to deal with angles, where you need to use the statements to match up the correct congruent angles, finding a missing angle if necessary, or you'll be given sides, where you need to set up the correct proportions. And the easiest way to do that is look for the triangle. Go to the triangle that has both the variables, or at the very least one of the variables, and match up the known side, because they have to give you a known side, otherwise you can't solve these. So you match up that known side of 12 to where it belongs. RT matched with ML, that's why I matched with 4. And then we just picked one of the variables for one fraction and the other variable for the other equation. Okay, so that's it for this section. So next time we're just going to practice a little bit more with solving of those similar triangles I'm involved with. I'm going to tell you the triangles are congruent, solve for missing sides and angles. So I will see you next time.